Hello, everyone. Thank you for joining me here today. My name is Jolene, and I'm here to talk to you about the Modern Sanitation Landfill Superfund site. The agenda includes the site history, site status, a summary of the contaminants, human health and environmental impacts, and we'll wrap up with risk management recommendations. Here we see an aerial photo of the landfill taken from the local news. As you can see, it is quite massive. Today, it is the tallest point in the county. The Modern Sanitation Landfill, located in York County, Pennsylvania, has been operational since the early 1940s. While it primarily accepted municipal and non-hazardous waste, the site also handled hazardous industrial materials, including PCB wastes, pesticide sludge, and heavy metals. Contamination issues were first identified in the late 1970s and the early 1980s. In 1977, a groundwater interceptor trench was built to manage leachate, and by 1981, the state detected volatile organic compounds, known as VOCs, in the groundwater. Further studies in 1985 revealed organic contamination on the eastern side of the site. Regulatory action intensified in 1987 when Modern Trash Removal of York Incorporated entered into a consent order with the Pennsylvania Department of Environmental Resources to conduct a remedial investigation and feasibility study. This led to the 1991 Record of Decision, which focused on the inactive, unlined 66-acre portion of the site. The selected remedy included completing a low permeability cap, expanding groundwater extraction systems, and maintaining an on-site wastewater treatment facility to mitigate risks to public health and the environment. Next, I'll discuss the site status. By 2000, the site achieved construction completion after the final 4 acres were capped. In 2015, the EPA updated cleanup goals to align with federal drinking water standards. Recent evaluations in 2025 indicate the remedy remains protective, though new monitoring for PFAS has been recommended to ensure long-term safety. The main contaminants found at the site are trichloroethene, vinyl chloride, benzene, carbon tetrachloride, and 1,2-dichloroethene. Vinyl chloride is a colorless flammable gas primarily used in the production of polyvinyl chloride, known as PVC plastics. In the environment, it is rarely a primary contaminant. Instead, it typically appears as a daughter product during the reductive dechlorination of parent solvents like trichloroethylene. From a toxicological perspective, vinyl chloride is a known human carcinogen that poses a multi-system threat, targeting the liver, immune system, and neurological functions. According to the 2025 5-year review, the fate and transport of vinyl chloride at the Modern Sanitation site are heavily controlled by aggressive engineering. To prevent the migration of contaminants into deeper drinking water aquifers, the EPA utilizes a 2,825-foot-long blast trench excavated 100 feet into the bedrock. This trench acts as a hydraulic barrier, capturing groundwater and directing it to an on-site treatment plant. The groundwater plume generally moves north-northwest, but the combination of the western blast trench and the eastern extraction system ensures the plume remains within property boundaries, protecting off-site residential wells. The risk of bioaccumulation in the local flora and fauna remains low. The landfill's low permeability cap prevents waste from contacting surface water or soil, and historical studies of local fish and plants show no significant degradation. While recent testing detected PFAS in the treatment effluent, these levels currently remain below environmental safety thresholds. Regarding vapor intrusion, the EPA utilized the VISL, or Vapor Intrusion Screening Level, calculator to model potential air risks. The findings indicate that concentrations are currently below the danger zone for cancer or non-cancer hazards. Risk is further mitigated by gas extracting systems that remove vapors from the soil and the fact that no residential structures are situated directly above the plume. Although vinyl chloride is still being generated as parent compounds break down, the overall VOC levels are stable or declining, and the existing extraction systems continue to successfully capture these products before they can pose a risk to public health. Monitoring for PFAS or forever chemicals has been recommended recently. Next, I'll discuss human health impacts of these contaminants. It is clear that the current and future impacts on human health are driven by a complex mixture of volatile organic compounds. While these chemicals, trichloroethylene, known as TCE, vinyl chloride, carbon tetrachloride, and 1,2-dichloroethene, are often discussed individually, their presence in a commingled groundwater plume creates a significant synergistic risk for the local community. For example, benzene acts as a broad spectrum disruptor, interacting with thousands of genes to impact blood and bone marrow, whereas vinyl chloride demonstrates extreme potency by specifically targeting critical liver health pathways at even low exposure levels. The most concerning future impact involves how these chemicals interact with the human body. TCE, 1,2-dichloroethylene, and vinyl chloride are all metabolized by the same liver enzyme, CYP2E1. When residents are exposed to this cocktail via groundwater or vapor, this metabolic competition can overwhelm the liver and slow the detoxification of vinyl chloride. Furthermore, the combined presence of carbon tetrachloride and vinyl chloride implies that the risk of chronic liver disease is likely additive, meaning the total health risk to the population is the sum of these individual threats. Data suggests that as these chemicals break down, they become even more specific toward life-threatening outcomes like liver angiosarcoma. To protect long-term health, remediation and monitoring must address this integrated synergistic landscape rather than treating each contaminant in isolation. Here we can see a breakdown of these 5 contaminants in relation to gene interactions linked to diseases and their biological pathways. Next, I'll discuss the environmental impacts that originate from the Superfund site. Modern sanitation landfill presents a complex toxicological puzzle where the physiological properties of VOCs determine their environmental behavior. My analysis is focused on the mobility and bioaccumulation potential of 5 primary contaminants: trichloroethylene, vinyl chloride, benzene, carbon tetrachloride, and 1,2-trichloroethene. Currently, the site faces 2 distinct threats. Here we can see an overview of the data for the physical and regulatory metrics for modern sanitation landfills contaminants. First, highly soluble travelers like vinyl chloride and 1,2-dichloroethene move through the environment like ink in a stream, rapidly migrating towards Kreitz Creek and local groundwater. Second, stayers like carbon tetrachloride, which has the highest log count at 2.83, tend to stick to the sediment and build up in the fatty tissues of aquatic invertebrates. Next, I'll discuss the impacts on the environment. Carbon tetrachloride was previously used as a fumigant, but is now largely obsolete. It is moderately toxic to biodiversity and has low oral toxicity in mammals. The substance is considered carcinogenic and acetylcholinesterase inhibitor and a neurotoxin. Trichloroethylene and vinyl chloride are persistent environmental contaminants that enter aquatic ecosystems through industrial discharge and landfill leaching. Research on freshwater crustaceans reveals that even at environmentally relevant concentrations, these compounds cause significant sublethal damage. Vinyl chloride disrupts gene regulation related to metabolism and reproduction. TCE exposure is linked to altered molting patterns and decreased egg development. Beyond invertebrates, these toxins cause oxidative stress in clams, metabolic problems in fish embryos, and reduced phytoplankton density, threatening the stability of aquatic food webs. Benzene creates immediate and delayed toxicological risk across various aquatic trophic levels. Higher trophic species, such as certain fish species, demonstrate extreme sensitivity, suffering significant mortality during initial exposure. This makes them effective early sentinel species for detecting acute contamination. Invertebrates experience delayed impacts, including reduced survival of fecundity, though some reproductive recovery is possible over time. While algae and certain bottom dwellers appear more resilient, the varying susceptibility across species highlights how benzene disrupts community structure and reproductive health in freshwater systems. Trichloroethylene, or TCE, and tetrachloroethylene pose severe risks to regional groundwater quality. These organochlorines are highly mobile and persistent, often creating long-term contamination plumes. A critical environmental impact is the biodegradation of TCE into CIS-1,2-dichloroethylene, a toxic intermediate byproduct. This transformation demonstrates that even when original pollutant levels fluctuate, metabolic products can remain constant or proportional in the water supplies. The continuous presence of these chemicals and their derivatives in monitoring wells highlights their ability to linger in saturated zones, requiring decades of remedial oversight to protect local aquatic ecosystems. Looking toward the future, the most significant concern is the potential for synergistic effects. Because these VOCs often attack the same biological pathways, the cumulative stress could overwhelm the metabolic defenses of sentinel species. For instance, a high solubility chemical may act as a co-solvent, pulling stickier, more toxic substances deeper into the food chain than they would go alone. Protecting the local environment requires a remediation strategy that addresses both the fast-moving migrants and the persistent bioaccumulators. During various remediation strategies have been performed. Let's take a look at 4 of those studies. The field scale results from Chang et al. 2018 demonstrate that sodium persulfate oxidation can be highly effective in situ treatment method for TCE contaminated groundwater, making it directly applicable to Superfund landfill remediation scenarios. In the study, a 5% persulfate solution rapidly reduced TCE concentrations by 95 to 100% within 2 days of injection and was capable of migrating 3.6 to 4.5 meters through the aquifer, indicating strong subsurface deliverability for plume treatment. The oxidant persisted for up to 14 days, providing sustained degradation capacity, an important characteristic for addressing continuously migrating landfill plumes. Moreover, the study showed that while microbial populations temporarily declined, they recovered after oxidant depletion, suggesting that persulfate can be applied without long-term ecological disruption. These findings support the use of sodium persulfate as a practical field-ready technology for landfill-associated TCE plumes, offering both rapid contamination reduction and operational flexibility in real Superfund cleanup sites. The study by Fay et al. 2008 shows that in benzene-contaminated groundwater, microbial communities can shift toward gram-positive, solvent-tolerant degraders, such as Arthrobacter and Rhodococcus. When exposed to high benzene concentrations, with these organisms able to metabolize benzene at levels up to 600 milligrams per liter in groundwater and even 1,000 milligrams per liter in minimal medium. This adaptation demonstrates that natural attenuation processes may remain active even under extreme contamination, as these specialized bacteria outcompete gram-negative communities and continue degrading benzene to below detection limits. For Superfund landfill sites where benzene is a common leachate, this evidence supports incorporating monitored natural attenuation or MNA as part of a remediation strategy. Understanding that indigenous microbial communities can evolve to withstand and degrade high benzene loads helps site managers assess attenuation potential, design targeted monitoring plans, and determine whether bioremediation enhancement is necessary or whether natural processes are already functioning effectively within the plume. The investigation described by Gao et al. 2021 demonstrates how a structured multi-year approach to characterizing and managing groundwater contamination, beginning with source identification, plume delineation, and hydrogeologic assessment, supports effective remediation planning under CERCLA. Their use of detailed monitoring networks, contamination mapping, and performance testing of remedial technology, in this case a permeable reactive barrier system, mirrors the same investigative framework used at Superfund sites to address contaminants like carbon tetrachloride. By showing how contamination migration is tracked over time, how disposal history informs plume interpretation, and how risk based decisions guide remedy selection, the study provides a model directly applicable to landfill scenarios where legacy disposal areas often serve as long term sources to the groundwater. The systemic characterization and plume management approach, illustrated here, can therefore be used to design similarly robust investigations and remediation strategies for carbon tetrachloride releases at Superfund landfills. And finally, the findings of Liu et al. 2025 demonstrate that enhanced reductive dechlorination, or ERD, achieved by adding electron donors, such as yeast extract, can rapidly simulate anaerobic microbial communities to completely degrade carbon tetrachloride within 40 days, a significant improvement over natural attenuation alone. The study shows that electron donor additive drives strong reducing conditions, promotes the growth of key hydrogen producing microbes, and activates functional reduction dehalogenase genes involved in sequential CT dechlorination to chloroform and dichloromethane. In a Superfund landfill context, where CT releases often originate from historical disposal pits of degreasing waste, this approach could be used to accelerate plume remediation by injecting electron donors into the subsurface to stimulate native dechlorinating consortia. ERD offers a practical, field scalable strategy to reduce CT concentrations, enhance degradation pathways confirmed by genetic evidence, and shorten long term cleanup timelines under CERCLA. To wrap up our look at modern sanitation landfill Superfund site, it is clear that while the site has moved from an active hazard to a construction complete status, the toxicological story is far from over. Our management of this site must evolve from simply containing a plume to understanding the complex synergistic cocktail of VOCs that persist in the groundwater. Some key takeaways here are: first, the engineering success. The combination of the low permeability cap and the 2,800-foot blast trench serves as a vital hydraulic barrier, successfully keeping the plume within property boundaries and protecting residential wells. Additionally, toxicological synergy is at play here. We cannot view these contaminants in isolation. The metabolic competition for the CYP2E1 enzyme between TCE and phenyl chloride suggests the risk to human liver health may be additive or even synergistic, requiring a more integrated monitoring approach. Also, environmental sensitivity is a concern. While stairs like carbon tetrachloride accumulate in sediments, travelers like vinyl chloride threaten the stability of the Kreitz Creek food web by disrupting the metabolism and reproduction of aquatic sentinel species. My recommendations moving forward is for risk management to prioritize two areas. First is PFAS integration. As recommended in the 2025 5-year review, we must establish a baseline for forever chemicals to ensure our current treatment effluent remains safe. And for advanced remediation, we should consider transitioning from passive containment to active targeted treatments. Technologies like sodium persulfate oxidation for TCE hotspots and enhanced reductive dechlorination for carbon tetrachloride offer promising paths to significantly shorten the cleanup time. By treating the site as a dynamic biological and chemical landscape rather than just a managed landfill, we can ensure the long term protection of both York County residents and local ecosystems. Thank you for your time. I hope you've enjoyed learning in this presentation.